Did you know that one of the most fundamental experiments in modern physics was actually a failed one? The Michelson-Morley experiment pivoted our views in science as it changed how we see light and also helped prove Einstein's special theory of relativity. But how exactly did this failed experiment change the world? At least the world of physics. Well, to get there, we first have to start with the question. What is a wave? Well, what is a wave? The actual dictionary definition of a wave says that a wave is a periodic disturbance of the particles of a substance which may be propagated without net movement of the particles, such as in the passage of undulating motion, heat, or sound. Okay, that's a lot to unpack. So what it's saying pretty much is that a wave is a vibration, a vibration that propagates through a medium without the particles of that medium actually moving with the wave. Here's an example. Let's say you drop a rock into some water. When the rock falls through the surface, the water doesn't just pretend that nothing happened. No, the water reacts with a ripple. The rock has disturbed the water and caused the water to vibrate away from the rock, making the ripple a wave. And the wave doesn't carry the water particles with it. The water particles stay in the same lateral position and just bounce up and down. This is what a wave is. But why does knowing what a wave even matter? Well, the key point is that a wave needs a medium to travel. So for the water and the rock example, the water was the medium for the ripple to travel through. For sound, air is the medium that sound uses to travel because sound is just waves in the air. And at a sports stadium, the people doing the wave, well, the people are the medium of the wave in a sports stadium. But there's also another type of wave that you might have heard of. Light. At first, light was thought to be a particle after the works of Isaac Newton, and it was thought to be a particle until around the 1800s. Then, the famous double slit experiment was performed by the physicist Thomas Young in the 1800s, which proved that light was a wave. So let's assume that light is a wave, and by our definition, requires a medium that it propagates through. Because of this, scientists propose that there has to be some sort of special medium that permeates all of space, which light waves travel through, and they named this the luminiferous ether. However, this ether was not detected, so it was just a theory for now. But it wouldn't be for long. In 1887, two physicists, Albert Michelson and Edward Morley, banded together to create an experiment that would determine the velocity of the Earth going around the sun. They used a special instrument to try to determine this velocity called a Michelson interferometer. It works by shining a laser beam at a beam splitter that is at a 45-degree angle. The beam splitter is a half-silvered mirror, so it reflects half of the laser light and lets the other half of the light pass through the beam splitter. These two beams then travel an equal distance in perpendicular directions and reflect off of a mirror again. These two beams then return back to the beam splitter, and the same thing happens. One beam passes through while the other gets reflected. This makes the two beams recombine again and form the same beam as before, and that beam is detected by a photodetector. Okay, well, how do beams of light help us determine the velocity of the Earth? Well, let's look at what we're given. We know that the Earth is moving because it's in motion around the sun. And we know that there's an ether, the medium of light, that permeates all of space. Well, then this means that the Earth is traveling through the ether as it moves around the sun. Well, what does this mean? Well, if we look at it, we can see that if the Earth is moving through the medium in which a light wave propagates through, because of the Doppler effect, we can see that waves in the direction of the motion get bunched up. And waves going opposite the direction of motion are stretched out. And well, waves in the ether are light waves. So if we look at the experiment, we can see that the waves shot out in the direction of Earth's motion will be more compact and compressed than waves shot out in the opposite direction of Earth's motion, which means that whenever the waves recombine at the beam splitter and are detected by the photodetector, there are certain alterations or differences in the light than the light that was originally shot out by the laser. Using these differences, Michelson and Morley could detect the velocity of the Earth, because different velocities would result in different amounts of disturbances. However, when they actually performed this experiment, they found no significant disturbance, like at least not significant enough to prove that the Earth was even in motion, which is contradictory because we know that the Earth is in motion around the sun. So what could have gone wrong? Well, to try to see what went wrong, they performed the experiment multiple different times using multiple different interferometers and apparatuses and fixing every single interfering and confounding variable that they could. And yet, each time, they still found no disturbance in the light waves that the photodetector was detecting. This meant that something in the experiment that they were doing, like something fundamental, was wrong. And well, when they looked at all the other things, they were already proven, except for the ether. This experiment depended heavily on the concept that there was an ether and that the Earth was moving through the ether because it permeates all of space. And if they didn't find any result that concluded that the Earth was even moving, then there's a problem, because that just means the ether does not exist. So boom, there we go. The ether was disproven. However, the story doesn't end there. Remember the double slit experiment in the 1800s by Thomas Young? Yeah, well, that could not have happened unless light was a wave. But the Michelson-Morley experiment just proved that light can't be a wave because it doesn't have a medium to travel through. And better yet, Einstein's photoelectric effect, which he earned the Nobel Prize for, proved that light was a particle and not a wave. So what exactly is going on here? Well, it would take 50 years for French scientist Louis de Broglie to figure out that light was actually both a particle and a wave, a quantum mechanics concept known as wave-particle duality. Even though light experiences wave-particle duality, how does light act like a wave if it doesn't have a medium to travel through? Well, in quantum mechanics, light, or photons, are the mediators of the electromagnetic force. And the electromagnetic force consists of an electric field and a magnetic field. These two fields interact with each other to produce the electromagnetic force, and this force is what propels light through space. So it's really not traveling through a medium. The particles themselves are moving with the electromagnetic force. And this is known as a self-propagating wave. Because these two forces are interacting with each other on the photon, or the particle of light, it makes it act like a wave. But anyway, that's it for the failed experiment that disproved one of the biggest misconceptions in physics at the time. If you like this video, please consider subscribing and definitely hit that like, and I will see you in the next Square Root of Science video.